and the types of things I've done. And then the third portion of my talk is things I'm working on right now, the current research that I'm doing in this area. I would say in the last 10 years, those people who know me, I work on many different things, like most academics, and reliability, and mostly systems reliability and optimization of systems reliability. That's pretty much always been my primary research topic. It still is, it always will be. But in the last 10 years, I would say, this concept we're talking about today, this idea of a system of degrading components, that has been probably my number one research area. Now, I don't know how many people were here last week. If you were here last week, you already heard this, and even some of those who weren't here last week might already know this. In fact, I hope you do. But as Professor Shen said in the introduction, I come from Rutgers University. That's in the state of New Jersey. You see the map of the United States in the bottom with the red circle, and the state that is circled, that's New Jersey. And then you see it in yellow. And I work at the main campus of New Jersey. That's labeled at the map of Rutgers, New Brunswick. There's two smaller campuses, Rutgers Newark, Rutgers Camden, but they're small. The main campus of Rutgers, we're one of the largest universities in America. We're the State University of New Jersey, large public university, probably over 50,000 students. And we're also one of the very oldest universities. We're the 8th oldest university in the history of America. And we're in a good location. So when people can travel, and I don't travel at all, but when people travel, everyone listening is invited. It's a good location. We're very close to New York City, the biggest city in America. We're also close to Philadelphia, the 5th biggest city in America, and not far from Boston and Washington, D.C. and Baltimore. So it's a good place. Please come visit me sometime. Now, last week I talked about my research in combined system design and maintenance planning, where I work with some top researchers. This week, this is a different group, some overlap, but this is the group I work with in system reliability. My number one collaborator for 10 years and my number one co-author, I don't know how many papers we have together, a lot, would be Qianmei Feng, or Mei Feng, from the University of Houston. Now, also, have several very nice papers on degradation and reliability with Yisha Xiang, Texas Tech. And I'm not sure if people in the audience know what a career grant is, but a career grant is one of the most prestigious grants that the US National Science Foundation can give, and Professor Xiang was just recently awarded it. If you happen to know her, congratulate her. And finally, Hani Nassif, Professor Nassif, he's a civil engineering professor. And although today's talk is general, in the last year, almost all of my work, all my applied work, I should say, is with Professor Nassif. We're working on the reliability of bridges, and more specifically, the reinforced rebar that are used to make bridges, or make bridges reliable. And also students, and you see the picture there. Let's see, that picture is 2 years old. Looks like I have a beard then, just like I do now. But you see my current PhD students, they're kind of way in the back. Nooshin Yousefi is the woman with long hair, and Jian Zhou and next to him, Stamatis Tisyankis from Greece, and also fortunate to have Professor Gan working with us, and not in the picture, but Zhenhong Li, who has been a very, from Chengdu, very successful master's student, and then some previous students I acknowledge. Now here's my talk today. Again, the background, which will be a fairly good discussion. That's an introduction to this field, an introduction to system reliability, or really more specifically, an introduction to degradation modeling. Then I review some of my most famous papers on multiple dependent competing failure processes. Some of these are, they're old now, but they form the basis for everything that follows. So I'll review the mathematics and the theory in those papers. And those papers have led to many more papers, I mean, many. And given the title of today's talk, I primarily want to get into the multiple component systems. We have a very successful paper where a system is packaged together like a cell phone or an iPad or something like that. But a lot of our current research is systems that are not packaged together such that individual repair actions can take place. And that's a more practical, but also a more difficult problem. So first, we'll just talk, what do I mean? I'm an industrial engineering professor, although I also have a degree in mechanical engineering. That's my very first degree. So I have studied reliability and different failure mechanisms from a mechanical perspective, but that's quite frankly a long time ago. And now I'm a professor in industrial engineering. I teach optimization. This year I taught in the fall semester linear optimization, which I almost always do. In this most recent semester, I taught a class in nonlinear optimization, a PhD level class. And I taught a master's level class in applied optimization. So I work mostly optimization, but I have a background, strong background in reliability and also mechanical engineering. Now, I'm using the term, which most industrial engineers would, degradation in a general sense. What do I mean? Some process leading to failure which has observable and measurable deterioration such that you can observe it as it gets closer to a failed condition. Now, that would be many things we think of. That would be many of the products we use. What would be an example of something that does not degrade but still fails? Something that fails randomly and suddenly. Often electronics fail randomly and suddenly. They're working one day, they're not the next. Today's talk, however, is on things that degrade. We can watch them get worse. Hopefully we can measure them and compare some quantitative measure of their degradation to some thresholds. So what are some examples? I have a slide for each of these in no particular order. So I'll just go from top to bottom. But electronics, we usually don't think of as degrading, but there's some examples where they will as well. Batteries, which is a very kind of lately anyways, popular subject matter to study the reliability of batteries. And they degrade in terms of their charge and recharge cycles and how much they can charge. Concrete degradation, we're studying in bridges, metal corrosion, metal fatigue, wear, many others. Let me go more detail. Now, metal corrosion. This is you have some metal surface like the pictures show, and there'll be some form of oxidation, chemical reaction that takes place. And so, of course, in the design of these products, you try to prevent that. And that leads to some very interesting behavior. where the degradation takes place in two stages. Once the initiation of the corrosion, and then once the corrosion initiates, the propagation. And I will talk about that later. And the reason I'm going to talk about that later is the current project we're working on. We're working on a project on metal corrosion. I don't know what it's like in China, but in America, specifically New Jersey, where I live, we have lots of bridges. And I think the metric, the number I've seen, is up to 1/3 of the bridges. Many of them are very old. Could be considered unsafe to a certain degree. The concrete has cracked, or there's some other forms of degradation. To build a new bridge and make it strong, you have a metal rebar. You see on the left some pictures of the metal, different types of metal rebar, some samples, and they're encased inside the concrete. For about 1 year, we've been testing rebars and measuring the corrosion. You see in the middle picture some examples of corrosion. These are, and I'm actually not, on the picture on the left, I'm not sure what the one is in the center, but we're studying the other 4 types. You have a black steel, which would be the most common. You can coat that with epoxy. Keep in mind, these are going to be inside concrete. But then stainless steel and the MMFX, they're would be more expensive and higher performance. And so the reason we're doing this testing is how much more reliable will they be? In other words, are they worth it? And on the right, you see that's Rutgers IE student Jen Hong Lee. I think I saw he might be listening. It's not a real picture, he's just kind of posing. So related to the rebar, which is metal corrosion, now you have concrete degradation. So you have the concrete itself is degrading, cracking basically. But as the concrete cracks, moisture and pollutants and other things can permeate into the concrete. And of course, that's when perhaps the rebar would. Metal fatigue due to stress cycles. And an example of that is here. This is some testing. Qianmei Feng from the University of Houston and I had a very successful National Science Foundation grant. And her university, the University of Houston, the manufacturer of stents donated, not the stents themselves, but some test samples of the material. And then she was able to solicit funds from the state of Texas to pay for some testing. And so this is the actual testing done for our project to look at the metal fatigue of the stents. If you don't know what a stent is, and perhaps you don't know the English word, a stent is something that goes into the human body, goes into your vein to keep the vein from closing. So very important. And in fact, we wrote one paper treating the human body with multiple stents as a system of degrading stents. Of course, there's wear that we're all familiar with. Anyone who drives a car has wear on their tires or on their bicycle tires. Many other things, many other surfaces that wear. Battery degradation, I'm not exactly sure all the reasons why, but right now, very trendy in America to do work on battery reliability. And how they often measure the reliability is what percentage of the original capacity when you recharge the battery, like of your phone. And that amount will continue to decrease until the performance is so poor, it's considered a failure. Now, I include this slide just to be complete, and also to show that degradation is not necessarily limited to mechanical type failure mechanisms. There's also some electrical. Now, I want to make a real important point here. Of the failure of the degradation failure mechanisms I showed, many of them, fatigue, corrosion, wear, they're monotonic. What do I mean by monotonic? They don't get better. They only move in one direction. They get worse. The wear on a tire tread, it gets worse. It doesn't get better. That's an important concept, monotonic failure. Now, the ones we're looking at now, electrical and electronic component, they may not be monotonic. There may be a lot of random noise together with the degradation signal. So that's an important distinction. Why is it? Well, the choice of degradation model is important, and some models are monotonic and some are not. And so the choice of model should match the failure mechanisms. In my studies, all of them, well, no, not all of them, but most of them are dealing with monotonic failure mechanisms. Now, we'll talk about what do I do with those? Well, consider the simplest graph here. We have x of t is this measure of degradation. Again, it could be any of the examples I showed you. Where, something else. It could be a surrogate measure, meaning you can't observe the degradation directly. So you're taking some sort of a measurement that gives an indication of the degradation. And we see some horizontal line there marked H, failure threshold. And then we see these different paths. And when each individual path, when it shows it's crossed the threshold, that's a failure. And then you see those the three blue distributions. This is a two-dimensional plot, but imagine if I lean those up so it's three-dimensional. That shows that any time there's a distribution of the degradation measures, and here I use capital G, it could be anything. It's a distribution. I say xt is distributed as G with, I said, a mean and some variance. In the typical example there, I showed the variance is increasing. It could be constant, it could be increasing, maybe something else. So this is what we mean, that when these degradation paths cross the failure threshold, that's when there's a failure. Now, let's review, back up. I've been a professor 20 years, more than 20 years. Teach reliability. I did research in reliability even before I became a professor. And let's kind of summarize different approaches. What's the traditional approach? If you buy a textbook in reliability, or you attended, actually I haven't been teaching reliability lately, but I used to. If you attended my class, I would give you the traditional approach. What is that? I collect data of time to failure. I fit some distribution, exponential, variable, gamma, something else. And then I use that information to construct a system level model. I make certain assumptions. I assume it's a homogeneous population. I assume the failure times of components are independent. And I have a model. Is that a good approach? Well, sure it is. Are the assumptions always correct? No. The failure times might not be independent. The populations might not be homogeneous. But what's another deficiency? Mostly we study the reliability of things that are already reliable. Does that sound wrong? But it's very true. If something's not reliable, often it's sold for price, and or maybe it has a due to the change of technology, it's not anticipated to be used very long. When we study reliability, often we're studying things that are already reliable. So you might say, well, if they're already reliable, why study it? Well, it's because they're really important. They're really important. And because they're already reliable, it's hard to get data. Okay, so that's an issue. You have other researchers, say University of Maryland has the center, the Kelsey Center. They have a different approach. They say, look, don't necessarily collect data. Instead, study very specifically the failure mechanisms. And if you really know the failure mechanisms and you construct a physical model, you can design a more reliable product. Well, sure, who can argue with that? But the issue is a complex system may have many failure mechanisms, and these physical models may not be available. Also, the physical models might be deterministic. Now, mechanical engineers, and I have a degree in mechanical engineering, are happy with deterministic assumptions. But, and I don't know my audience, I know some of them, those of us who are industrial engineers usually are not happy making deterministic assumptions when the behavior is probabilistic. So that brings us to degradation models, which is today's talk. So I have this observable and measurable loss of performance, and I'm gonna characterize that or model that as some sort of a stochastic process. Why? What are the benefits of that? Well, many. One, look at the picture at the bottom part of my screen. I had the circle means it did not fail. The star means it did fail. So I have 5 items on test, 2 failures, 3 that were censored. They did not fail. That's not much data. What can I do with 2 failures? But if I'm going to have a degradation model, I can collect data on the same component on test multiple times. And I can collect data like the upper one and the lower one before it fails and use that data in order to establish a trend. Again, if there is some degradation mechanism. Second, I can use the degradation model for condition-based maintenance. And let me add also, not on my slide, but for predictive maintenance, where if you're not aware, a failure time distribution doesn't really give me that benefit. It tells me when it's going to fail probabilistically, but not when it's a good time to do maintenance. I can do time-based maintenance based on a failure time, but the most cost-effective maintenance is condition-based maintenance. When the degradation deteriorates to some unacceptable level, but has not failed, it's a good time to replace it. The final one, which I guess you won't really see today, but I plan to give a much more specific talk at the conference in Xi'an in October that will go into much more detail into some of my current models, where if we have this stochastic process, we can have the parameters of that process then be a function of different stress or design variables. And I can begin to customize my model such that maybe in one geographic location, the model is different than another, and so more benefits. I don't know if Bill Meeker wrote the very first paper. It's certainly the first paper that popularized this idea of degradation models. Bill and I both happen to be natives of New York State, and he wrote this paper in 1993, Liu and Meeker, in Technometrics. And I could be wrong, but other than a few statisticians, I'm not sure a whole lot of people read it. But they did eventually. They did eventually. And it took a while, but 10 years or so after that paper was written, lots of people read it. And so, so I give him credit, certainly for popularizing it. I sent Bill some emails to asking him once, Bill is short for William, if you don't know. I suppose I should say Professor Meeker. I sent him some emails once, said, well, how did you think of this idea at the beginning? And he had been working at Bell Labs and and was able to work on this. And he's been a professor at Iowa State for, I don't know, 45 years, I think. And I'll add, he's a speaker at the APARM conference he's one of the keynote speakers at the APARM conference in next month in August. That was intended to be in Vancouver. Now it's online, and I doubt they're listening, maybe. But the organizers, Ming Zhou, Stephen Lee, they've done a tremendous job. So I would encourage anybody. They got they got speakers: Meeker, Wei Kuo, Andrew Jardine, tutorial speakers. I will give one: Enrico Zio, Cal Kapoor. So anyways, that's my advertisement for APARM. Now, degradation models. Before I talked about monotonic versus non-monotonic. So there's many choices. Meeker's original model, which now we can look back and say, well, kind of simple. And it has various names, but I call that the random effects model. I have some degradation equation, and I treat the parameters of that equation as random variables. And that gives me this distribution. And many of my early papers took this approach. A gamma process is another very popular. Most of my current work uses the gamma process. That means between any 2 points in time, the difference in this measurable degradation follows a gamma distribution. But the time goes on. A Wiener process, which is based on Brownian motion, that's non-monotonic. Inverse Gaussian process, popularized by Jisheng Yi and his students with a famous paper with Nanjing, and others as well. My talk today, though, not just my talk today, all my work, most of my work, the majority, not some current papers I'm working on, is the random effects or a gamma process. Okay, now so that's the first third of my talk, the background, and that's intended for a general audience. I don't really know my audience today. I can't see you, but feel free to send me an email later. Second part of my talk, I'll try to do quickly. This is my earliest work, the multiple dependent competing failure processes. But it's necessary to describe this because everything kind of starts from there. This is the work with Qianmei Feng, our first paper almost 10 years ago now, published in, at the time, IIE Transactions, now IISE Transactions. And this is the first time we introduced this concept of multiple dependent competing failure processes. This paper has also with Hao who is in Beijing now. This paper has been very widely received. In fact, on Web of Science, this is my third most highly cited papers. And you might think third, well, why not first? Well, I don't want to brag, but my most highly cited paper has the most citations in the history of the Journal of Engineering and System Safety. That's a kind of a tutorial paper. And my second most highly cited paper has the second most citations in the history of the journal IEEE Transactions on Reliability. So this is third. This is third. So it's well received. If you look at the graph, well, let me skip ahead. Well, I guess to do it here. You see two graphs, X of T and W of T. Those are two failure processes that are competing and dependent. I'll define both of those later. So the same component can fail due to two of these processes. There could be more than two. It could be generalized. But we picked one that was a shock process on the bottom and one that was a degradation process. However, you see something a little different. When the shocks occur on the bottom, there's also some incremental change along the top. And notice those vertical lines, they line up. So when there's a shock, there's also incremental damage to the degradation process. Now, in this paper, we use the terms hard failure, soft failure. Let me go on record of saying I don't particularly like those terms. We didn't invent them. They've been introduced by other people. We use these terms, and they're a convenient mechanism. I don't really know exactly what it means, hard and soft. I mean, hard like my table and soft like my pillow. But the way they're used is this. Soft failure means what we've been talking about, a failure that occurs due to gradual degradation. You can observe it getting worse. And because you can observe it getting worse, you potentially can prevent it. Hard failure, something that happens suddenly without warning. Let me move ahead, but from our first couple papers, we used this MEMS oscillator. We were very lucky. We got some data from Sandia National Laboratories, and most of our early papers used this MEMS oscillator. It started just as one pinhole of the MEMS oscillator, so very, very small mechanical device subject to both hard and soft failure. So here's the graphs again. As time goes on, these two failure processes, they're competing. What does that mean? They're competing just like if you were running a race, and whoever wins the race is the winner, or whoever gets to the finish line is the winner. Here, the two failure processes are competing to see which one can cause the failure. So you can have a soft failure, meaning you've passed that threshold, or a hard failure. So you notice when the soft failure occurs, a new component where the degradation went down to zero, or replacement was used. So in the first cycle, it failed soft. The second failure, it failed hard. Now, so we defined competing, and our first paper was just, we show this whole MEMS device here, but our study was just on the pinhole. So you see in the lower left, the gear and the pin joint. And we were just studying failure of that pinhole. It was degrading as the MEMS was being used, but it was also subject to shocks that would cause sudden failure. This is a very small device. So for the part to survive, it had to have no hard failure, but when it received a shock, it also affected the degradation. And that created dependency. Meaning, for example, if it was subject just randomly to a lot of shocks, it's more likely to fail hard, but also more likely to fail soft because there would be more of those incremental failure damages. So it's supposed to be an animation here. It didn't work. That's okay. But we see as time goes on, the shocks occur. It could occur as a Poisson, homogeneous Poisson process, maybe something else, but for each individual shock, we have a assumed, or hopefully based on something, probability density function for the shock magnitude. And we also have a failure threshold labeled D. Now, we don't know how many shocks there'll be in a given time. It's a random variable. But each individual shock, it would just be the cumulative distribution function evaluated at D. I say here, for example, if it's a normal distribution, D minus the mean divided by the square root of the variance. Could be any distribution, however. Now, the soft failure, we have X subscript S. So it's equal to the smooth degradation plus the sum of the shock damages. So Y is the shock damage. Here's the important thing to notice. So S of T is the sum of the shock damages. Here's the important thing to notice. NT is a random variable, meaning this is a sum of a random number of shock damages. So that makes it harder. Now we combine those together, and having a little trouble with my PowerPoint. And let's look at these equations one at a time. First, a cumulative distribution function for total degradation. It's the sum of x, the smooth degradation, and those shocks. Well, the shocks are based on a random number of damages. But in the second equation, I can condition on the number of shocks and then sum over the number. Why is that so critical? Well, because now the S of t is conditional on n of t, I can know. For example, the sum of normal distributions is also normal. The sum of gamma distributions is also gamma. So these often can be standard distributions. Third equation, I just put S of t on the other side of the less than sign, y. That's a random variable, but I can then condition on that and integrate. And the fourth equation, you see this convolution integral. And that's the key. That's what makes this possible. I need to integrate over this cumulative damage due to n shocks, and then I'm summing over n. I can then take that and construct my reliability equation. Needs to survive all of the n shocks, keeping in mind I'm summing from n, and I'm having some PowerPoint difficulties. That's probably my fault. I made a mistake. And that gives us, so what was supposed to happen with the animation was then, there it goes. I don't know what's going on. So it shows the hard failure and then the soft. And then finally, that's the important equation. Notice there's no distributional assumptions. This could be for any distribution for all of the parameters. W could have any distribution. That's a cumulative distribution. Even at the far right, I'm going to later assume it's a homogeneous Poisson process, which means that that probability will be Poisson, but it could be something else. And then in the middle, G could be normal, could be something else. So that's the most important equation in that paper. Here's an example from the paper, and I sometimes get annoyed, so please don't do this. Because the example made certain assumptions, people think the paper was limited to that assumptions, and it was not. In the example, we could have a normally distributed degradation, homogeneous Poisson process, and we can easily then get a reliability equation. If there's no shocks, keep in mind we're summing, it's just the probability that the pure degradation is less than the threshold H, and then we sum over the others. Okay, let's move on. Now that we got the first paper done, and it was very well received, we started to extend it. And I'm going too slow once again, so I need to do this quickly. The first extension was, we wanted to make more complex shock behavior. So if we have different types of shocks, extreme shocks, delta shocks, M shock model, that if it's exposed to these different types of shocks, potentially, as you see in the graph, the failure threshold would go down. This was mostly done by a University of Houston student, Lei Jiang. Similarly, and this was actually, this whole paper came from, I think I was in a conference in either Chengdu or Xi'an, and Enrico Zio asked a question. He said, well, why can't you do this? And so I went back and we did it. And this is the degradation rate will increase if the shocks patterns exceed D0 in the lower graph. And you could think of it, I told my students, I'm a fan of boxing, where two men or women punch each other. And if the punches are hard, but not hard enough to severely damage, but still the opponent will be weakened, and the rate with which they get damaged more will increase. Another extension, we said the shocks could be in different categories. Look at the bottom graph. We could have safety zone, no effect, no effect. a damage zone. They do have effect on the degradation, but not critical. And then a fatal zone. So that was another paper, also primarily by Lei Jian. Now, this is what I wanted to talk about. I could use the rest of the time on this, but I won't. Our next extension, we wanted to move this into two-stage degradation models. This was inspired by our work on the concrete bridges and the metal rebar. We've written 2 papers. They're ready to go. They're done. We're waiting for our civil engineering co-author, and they're 2 stages because the corrosion of the metal rebar doesn't start. Keep in mind, it's inside concrete until there's been some sort of penetration, such that the moisture or the rain, which I guess is moisture, or the pollution can reach it. And so we have this initiation period. So my students started studying two-stage models. We see that the most impressive papers come from Professor Tui and his students at Beijing Institute of Technology. So we're using some of those you see along the bottom, some of those papers. And I see my friend Tao Yuan has a paper where he uses hazard rates that will shift. So we realized the work we did needs to be modeled that way. And we had lots of data, still do. 2 different types of concrete, 4 different types of steel rebars. We want to accelerate. The reason we're doing this study is so we can accelerate failure in the laboratory, so we can then make judgments about the reliability of these rebars that are going to be used in the bridges over a long, long period of time. How do we accelerate? 2 ways. We increase chloride concentrations, which will mimic the exposure to chemicals out in the field. And then we can pre-crack the concrete to get the corrosion to start earlier. Now, that's of no good unless we can then mathematically translate what it means with the pre-cracked concrete to actual behavior. And so that was our study. And this is examples of the rebars, and these are the test facilities and some of the data. This is all the data we have. And there's a lot of noise in this data, but consistently you see the 2 stages. It starts, it turns a corner. It starts at a low rate, turns a corner. We developed a new model. Because stage 1 for us, we thought would be better modeled with a time to event distribution, the time until the corrosion was initiated, or the time to latency. And so our first stage, T1, is simply a Weibull distribution of time to event, like a Weibull failure distribution. But once the corrosion starts, we shift to a degradation stochastic process, which is a gamma process. So instead of a gamma-gamma, which we did, or a Wiener-Wiener, we actually have a Weibull gamma 2-stage model. This is very new work going on like right now. I'm not going to go over this equation, or else we'll be here all night. But we can develop this equation where stage 1 is a Weibull time to event distribution. So we don't know when the corrosion is going to start. It's a random variable. So at some point, we're going to need to condition and integrate over the probability density function of T1. Now, both stage 1 and stage 2 are a function of stress covariates. Stage 1 has stress covariates, which for us was the size of the initial cracks. They're, of course, going to influence when the corrosion starts, and also the chloride concentration. And then stage 2, which is in yellow, those are the stress variables that influence the rate of corrosion once it starts. Chloride was in both vectors. Okay, let me move on. And we can use this to make accelerated life testing plans. And some more. Now, I meant to get to this sooner, but we then take the system, the component, put it together in a system. Now the shocks come, but the shock comes to the whole system, not the individual components. So this creates a more complex model. So we have this paper by primarily Sanling Song, part of her PhD. Sanling Song now works for Aptiv, which makes self-driving, I think, software for self-driving cars, where we took what we already talked about and built it up to the system level. Now, this is more complicated than you might think. For the system to be reliable, and this example is for a series system, but I could do this for anything. I mean, it gets pretty complicated if it's a complex system, but I can demonstrate it for series, but we could do it for parallel or something else. But notice the intersect symbol, because the component reliabilities are clearly not independent. Why? Because the shocks hit the whole system. So NT, which is the number of shocks, is a random variable. And NT appears on both failure processes for all components. So think about it. If just randomly NT is high, and it's a random variable, so it might be, each component is more likely to fail due to hard and soft. So everything is dependent. And I'm using the word dependent, and not everyone likes this. I might say S-dependent if I was writing for IEEE transactions on reliability. But what do I mean by dependent? They're not independent. In other words, the covariance at some time t for any two components degradation is not zero. And so each component, the two failure processes are dependent, but also the components themselves, the failure events are dependent. But I can condition. So you notice the sum comes first, always. I can condition on the number of failures. Now, for every term of the sum, there's conditionally anyways a fixed number of shocks, which then makes the math easy. I can then also take the sum of the y's, that's the shock damages, create these convolution integrals, and compute the reliability. First, it needs to survive the hard. And I have this general equation. Again, this is for series, but I could do it for other structures as well. So this is for a system. Now that's a hard integral to solve, by the way, and we need to solve it numerically. But still, this gives the reliability performance. As I said before, normally, traditionally, people assume independent. So let's compare. This is an example with a high number of shocks. It's not a real example. We manufactured this example to show the difference. So we have a high number of shocks arriving, which makes the difference between whether it's independent or dependent a lot. So again, this is not a real example. We increased lambda to make a point. But what you see here is if I had assumed they were independent, I would actually, and I know this is counterintuitive, but I would assume the reliability is much worse than if I model it as dependent. You might say, worse? I thought it would be better. No. Think about it in the extreme. If all components were dependent, very dependent, I could model the whole system as if it was just one component, let's say the worst component, because all the others would behave similarly. So when you assume a series system, the components are independent, you're actually being pessimistic. Okay, let's move on. First extension we did, we say, look, there's different types of shocks. They're not all the same. If you have an automobile, you could have shocks, different geographic locations. So we extended this to a paper on shock sets. The next extension we did we said we had made some simplifying assumptions in the previous, all these papers, I'm sorry, all these papers I'm talking about right now, the system is packaged together. So think of your phone. Your phone has lots of components, cameras, microphones, a screen, electronics, but they're packaged together. My students tell me they will pay someone to repair maybe individual components, but for many of us, if our phone has failed, we'll get a new one. Your iPad, if you have one, other things. So they're packaged together. It's not convenient to replace the individual components within that system, although there are components. So these first papers are on systems that are packaged together. All of these papers. Okay, notice, multiple component systems packaged together. This is shock sets. Our next extension, we wanted to model more accurate behavior on the distributions of the shock damages. I didn't make a big point of it, but in the previous paper, we said the shock damage, those Y variables, are independent. The failure processes are not independent, but the amount of shock damage in each individual shock is independent, meaning component 1 and component 2 has independent shock damages. Well, that didn't seem too realistic, and so I asked my student, let's try to fix that. And we then wrote this other paper that is 2016. And we made it kind of a simple model. Now notice, when the shock comes in, that's ZS, it comes to the whole system, not to the individual components. But what we want is ZJ, I should say, to be the shock magnitude for the whole system. But then there's a transmission till it reaches the components. And we use these simple equations down here. Unfortunately, there's a small typo. The beta should just be beta subscript I. So we have a transmission to each component I, but J is the jth shock to the system. So alpha and beta dictate, or just what is the amount of protection. If alpha and beta are low, the shock sizes won't be that big to the components. The next extension, just accepted in a journal, we said there could be more forms of dependency, and we say the different components, this is just accepted, I don't have a month yet, but in reliability engineering system safety, we say the components can degrade in clusters. What does that mean? It means as they're degrading, certain components within the system might be degrading as a group. Now, why would that be? Well, let's say one component, as it degrades, gets very hot, heats up, which will influence the components that are close to it. And so, which means they might degrade higher than anticipated too. And so this is a new paper. I think it's available, although there's no date on it yet. So we see that the components, in case 1, they're together as a group. In case 2, they're low. So now here's some simulation runs. These are the same 4 components with the same parameters. We notice blue and orange, they could be down with the rest of them, but they're always together. And yellow and purple are always together. Notice they're not randomly scattered. Wherever blue is, orange is somewhere nearby. And these were simulated based on our model. So this is, I don't know how common it is, but this is another advanced model. And this is Coit, I hope she's not listening. Yousefi is the first author. It's Yousefi, Coit, and Song. I'll need to fix that. Another new paper. I got this one right. Yousefi, Coit, Song, Qianmei Feng is still packaged together, But now we're going to select individual on-condition thresholds for each individual components. And this came out December 2019. And let me just go somewhat quickly, where this green line, the on-condition threshold, is actually our decision variable. We can move that up and down in order to get the most cost-effective preventive maintenance plan. Now, just like last week, I spent too much time talking in the early part. Now, what's some work that is ongoing? I had a master's student, Jingyu Chen from Chengdu, excellent master's student, back in China now. If anyone knows him, tell him I said good things about him. I gave Jingyu, I said, we have these models of systems that are packaged together. There's many systems not like that. Let's think of a system like railroad tracks. You wouldn't replace all the pieces of the railroad track, you'd replace them individually. So he wrote a very good thesis on this, and imagine this picture in the center of the screen. Now we're inspecting tau, 2 tau, 3 tau, and we don't know a failure occurs until we detect, and the X means a failure. But when we detect a failure, we just replace that component that failed, like the railroad tracks. You imagine the system is a system of railroad tracks. Now, we assume at the beginning of this system, all the components are new. But after a while, we start doing these replacements that in one interval, one inspection interval, you're going to have a mix of old and new components together. Yet, even though there's old and new, their degradation paths are still dependent due to the shock processes. So it's a different form of a problem. And so what we chose to do is we say we're going to wait till we're in steady state. Steady state is the gray, which means we're going to wait until at the beginning of this inspection interval, the start times of the components are independent with respect to each other. So you got some new, some old. For example, at the beginning, they would not be. They'd all be new. And in the second one, most would be new. But eventually, as they go through many replacement cycles, and then our optimization problem was then to minimize the cost rate in an interval during steady state. And that was his thesis. Zheng Yu and Nooshin Yousefi have written a very nice paper. It's sitting on my desk to finish. Probably by the end of 2020, I will have submitted that to a journal. My students write too many papers. I can't keep up with them. Now, if you look, let me go to the next slide. Or let me do it here. So now, if you look, that's too hard to explain. But at the beginning of the cycle, you have 3 components now. Okay, here you see it here. You have X of T, but that's T, here T is just the inspection interval time. And you have UI, which is the amount of degradation at the beginning of the threshold. So it's a random variable. And then you have S, which is, again, the shocks, but just the shocks in that inspection interval. Now, Jingyu did a lot of time figuring, well, what's the distribution of U? And under certain assumptions, and look at this graph in the middle here, at the beginning, they're all low. And then they age together, but little by little, they start to get replaced. And so the average over many simulation runs starts to decrease, but then eventually reaches some steady state. Meaning way out in the future, if you randomly select, it could be anywhere in that interval. And under certain assumptions, and not all assumptions, it will be a uniform distribution. Now, we submitted this to RESS and actually got a pretty good review. But then I withdrew the paper. So maybe one of the reviewers is listening to me now. I withdrew the paper. Why? I thought of a better way to do it. I thought of a better way to do it. I want to get an analytical distribution for you. So I withdrew the paper, and we're finishing it up, and we'll submit it again. Because this is the key part. What is the distribution of the degradation at the beginning of the interval for each component? Now, I'll try to wrap this up pretty soon. And we did many simulations, and you can see it is somewhat uniform, but only under certain assumptions, only under certain assumptions. And that's what bothered me, because I had to introduce some assumptions that may not really apply in some examples. So we're finishing this up again. Now, let me maybe make this the last one. This is another paper, 2000 XXX, Yousefi and Coit, I think just the two of us. Now, and this let me think. At the MMR conference, I presented a very early version of this in Hong Kong last year. Now I want it to be dynamic. The previous model was static, meaning I'm going to get an optimal inspection interval and just always use that interval. I'm going to get a optimal on-condition threshold and always use this. I'm saying for this paper, and Nooshin Yousefi, my student, no. Every time I inspect it, I can customize and dynamically select the next inspection. Look at the graph on the left. You see the green vertical lines, that's inspection. And for example, if I inspect and all the components have degradation close to 0, I don't need to inspect again for a while. On the other hand, if they're close to the failure threshold, I better inspect again soon. And so we did different versions of this. Every time we inspect, it's a difficult optimization problem. And we thought, well, that's not very practical. These are some hard problems to solve. It's not really very practical. If someone really wants to use this, I can't ask a technician in the field to solve a difficult optimization. And I mean, real difficult. You know, these are non-convex, intractable objective functions, certainly highly nonlinear. So what we decided to do is, before we started, we tested and simulated and did solve analytically over a wide range of possible problem parameters. And we trained a neural network to mimic that behavior. So the neural network could output the results of those optimal, optimal solutions to those difficult optimization problems. So you see here the black box. So our first version, which I presented at MMR, and like all good professors, I shouldn't say that. I don't want to present my very best work because I know that's going to go to a journal. But at MMR, we just output inspection time. When should I do it next? But the paper that we're almost done, in fact, it's sitting on my desk, is we're going to, in each inspection interval, solve a problem. When should I inspect next? And what should the next on-condition thresholds be? And if you are wondering why should they even change, there's always a relationship. If I'm going to wait a long time to inspect, I have to lower those thresholds. Don't have to, but it often makes sense because I want to be, if I'm not going to look at this again for a while, I better replace it before it's even close to failure. On the other hand, if I'm going to inspect very rapidly, I know I'm going to see this again soon, and so I can put the thresholds up close to the failure thresholds. Nevertheless, we solved this many times, put the results in a black box, trained a neural network, so we have a machine learning type output, and you can see on the left, when it's new, this is just two components, red and blue. When it's new, we're going to go a long time before we inspect. We observe these degradation amounts. They go into the neural network. It says, oh, we're about halfway to the failure, better look at it sooner. But because we're looking at it sooner, it's also changing these thresholds. Now, some of those behaviors are predictable, but then red is replaced. So now in my system, I've got an old one and a new one together. And often very hard to understand exactly the solutions. But now you see we have a purely dynamic model. You look at the graph in the right, these are three different objective functions based on what I observe. On the bottom one, U1, I'm sorry, there's three, looks like I only show two components on the left, but the graph on the right has three components. We see U1 equals 0, U2 equals 0, U3 equals 0. That means the observed degradation at the beginning of an inspection interval. Well, I don't need to look at that for a long time. And we notice the minimization takes place over here. And then on the other hand, these are two different curves. So it's going to be a purely dynamic model. Every time I inspect, I'm going to get a new time to inspect the next one. I've already gone an hour and 10 minutes, so let me wrap this up. Here's some applications. We've had the paper on stents, on some other behavior, and a paper with Yisha Xiang on performance-based contracting. Ongoing research. Let me finish this up. We already have this paper. I know it's really, we put it in for a special issue. This is our first paper on reinforcement learning. Again, this is going to be a dynamic model. I'll be glad to send this paper to anyone, but I want to tell you our best papers are still coming. So this was some preliminary results. No, they're not preliminary. These are some good results. We're kind of lucky to get this early version of the paper published. But we have Markov decision processes, which then are used to dynamically say, when will what should I do given this current state of the components? And I'm mostly learning from my students on this, so this is new to me. And then the final thing I talk about is, and I'm very interested in this, opportunistic maintenance. We have one paper already. Look at these wind turbines. We see the electrical generator failed. Which means that triggers a repair action, which means I have opportunities, maybe, to do preventive maintenance on the things nearby. Now, I'm not going to do preventive maintenance if they're still as new, but it gives me the opportunity to economically perhaps do some preventive maintenance. And that concludes my talk today. Oops, wrong button.
Okay, thanks. Thanks, Darren.
Once again, I think I did better. Last week I went 4 hours and a half, and I'm sure. So this week I tried to keep it to an hour and 15, and so I guess I achieved that. But still a long time for you to listen to me, particularly listening online. So. And then I'm very serious. I don't really know who's listening, but as many people know, I think I've lectured probably at, I need to make a list. I'm going to say at least 15 different universities in China. I always welcome questions. Always welcome questions. I'm busy like everyone else. Might not be able to answer right away. But always, if somebody's interested in my work, always happy to have them ask me a question.
Yeah, thanks, David. And I know that we have some time left, and then if anyone have questions, and you can ask Professor Coit.
Hello, Professor Coit.
Yes.
Can you hear me?
Yes.
I'm PhD student in Nanjing University of Science and Technology, and now I'm a visiting student in the University of Arkansas following Professor Hao Peng.
I know him. I know him for about 20 years.
Yeah. I have one question. My research topic focuses on the imperfect inspection, and now most researchers take the imperfect inspection into maintenance management when a system follows a discrete degradation process model like a billion time model or micro model. And the fewer researchers take the imperfect inspection into the continuous degradation process model. Could you give me some comments if the imperfect inspection can be taken into the continuous degradation process model?
Yeah, so great question. And we're working on that, and we have not solved that. In fact, my student, you saw the name Yousefi in many places, Nooshin Yousefi. She's a PhD student who has done most of the recent work in this area. And in her PhD proposal, she proposed that that would be one of the tasks she worked on, imperfect maintenance. And we've been working on that, and we finally have an approach, but we have found that to be difficult. And the approach we're taking, in fact, she's written a paper, I haven't even looked at it yet. It's with Professor Jiang and our visiting scholar, where we've discretized. We've taken the continuous degradation process, which is really what we want. But just like you said, it's difficult to do, but we've discretized it to discrete states. And then we've modeled it as imperfect maintenance. And again, I haven't actually even seen the paper other than the title. But by returning not to the as good as new state, but to a less perfect state. But I very much would like to do imperfect maintenance, continuing to treat it as a continuous random variable. But I have not figured out how to do that yet.
Yeah, maybe maybe you can after the lecture, maybe you can send some of your papers to Professor Coit, and then maybe he can give you more detailed comments and suggestions, I think. So
Okay.
Is that okay, Professor Coit?
Of course. Of course.
Yeah, thanks very much.
And tell Professor Hao I say hello.
Okay. Okay. Professor, bye.
Yeah, we still have some time to have more questions. Oh, someone asked that, Qianmei Feng have asked one question in the chat room, and he asked, your presentation benefits me a lot, greatly appreciated. Could you please kindly introduce some typical dependence modeling methods in degradation? Thanks. From the question from Qianmei Feng.
And thank you. So yeah, that's, I know what we did. Now, I know there goes my work. I think she might be listening. Well, at Beihang, we've looked at different approaches. I mean, a traditional approach would be the use of the Coppola function. But that's difficult because there's many Coppola functions, and you don't know which one to choose, and you don't know really how to customize it or parameterize it. But that would work. That would work. If you know, and I'm assuming you do, because I think I referenced the paper in my talk today. But The cupola function, of course, you take the two distribution functions and multiply it by the cupola function to introduce the dependence. Now, there's no question in my mind you could get that to work. Now that would be probably so that's one answer to the question. That would be a way to do it. Now, in my clustering paper, I did not do it that way. Instead, what I did was I had the individual components. They were each modeled in accordance to a random effect gamma process. So it's a gamma process. But the distribution parameters, for gamma, I always forget if that's the scale or the shape parameter, itself is a random variable. Now that's still not dependence, though. But the way it's a random variable is I made it a function, a mathematical function okay. So the parameter for the component gamma function is equal to a function of some random variable. And that random variable is shared by every member of the cluster. So if it goes up, all the members of that cluster will have that parameter be affected similarly. And then that creates, and we had to prove it for a reviewer, that creates a dependence such that the covariance is greater than 0. I don't know if I explained that properly, but if they're in the cluster, means they increase and decrease as a group. So even though each component has its own gamma process distribution parameters, they're equal to a mathematical function of this other random variable, and all the components of the cluster share it. And I don't know if that's a clear answer or not, but that's the way we did it. And it seems to work very well. Now, like I often do in my papers, you know the American slang term, I go overboard? That means I do too much. If I had just one cluster, that would be a good paper. But I said, well, there might be K clusters. And so the version of the paper that's going to be published shows the distribution parameters are not just a function of one random variable, but potentially up to K. Now, I kind of regret that now because it makes the paper much harder to understand. But nevertheless, that's what I did. So I said within a collection of n components in the system, instead of having one cluster, you could have many clusters. This group of components behave together, another group behave differently. So those are the only two ways I know to do it. Cupola function, well, I mean, I'm discarding the obvious way. You could have a joint distribution function, but that's not practical at all. Joint distribution function with time. Because mathematically you could do it, but how would you ever know what that was or estimate the parameters? So I don't think that's practical. But nevertheless, three ways to do it. Define a joint distribution function, a cupola function, and then the approach I took, which is have a random effect gamma process where the distribution parameters are a function of another random variable.
Okay.
I'll be glad to talk about it. Too bad I'm not in Beijing right now. Or we could talk tomorrow.
Yeah. It's very thanks. And for this question, I have a further question that so how can we measure the effects of the shocks and effects of the dependence in practice? I think it's very hard to measure the effect.
Yeah, absolutely. So a lot of my papers, like a lot of my papers in my whole career, trying to understand the behavior of these systems and have a mathematical model that matches the way they really behave. And so I think I've achieved that. But then I've introduced the new problem is to how am I going to actually estimate all those? And so that's the case of, I make the models, I'm trying not to do this, by the way. I make the models more complicated because it's closer to reality. but then they're harder to use.
Yeah.
Because sure, the more parameters there are, the more difficult they're going to be to estimate them all. So, but I lean on the side of, and maybe this sounds arrogant, look, I've got a new model that in my mind, it mimics the true behavior of the component. And therefore it's value. Now, you give me enough data, I can always estimate the parameters. But the truth is, as the model gets more complicated, it's very hard.
Yeah, I understand. Thanks very much. So, is there any questions or the audience? So maybe they are shy to ask questions, and maybe you can, after the lecture, you can communicate with Professor Coit by the emails or any other ways. I think it's Professor Coit will be very happy to answer your questions.
I'll be glad to.
Yeah.
And you could ask Professor Shen my email address. It's pretty easy. It's my last name. And I work at Rutgers University, so it's pretty easy to find.
Yeah, I know everyone.
Okay.
Yeah. Very thanks. Thanks very much for Professor Coit, and we'll see you next time.
Okay.
Thanks everyone.
Bye. It's 10 o'clock.
Yeah.
It's 10 o'clock in America, so I don't sleep yet, but thank you everyone for attending, and have a very nice day, and I'll say goodbye.
Yeah. Thanks, and have a nice drink. Thanks everyone. Thanks for coming.